problem is 76% of firefighters' deaths occur inside of a burning structure. And this happens because they don't know what's inside the burning structure until they actually enter the burning structure. So our mission was to create a robotic device that could go into the structure, collect data, wirelessly transmit it back to the department to give them an analysis before they actually enter the fire. What we came up with, our solution, is a completely fireproof module that will collect all of the critical data, oxygen content, CO2, combustible gases, and temperature, and then wirelessly transmit that back to the fire department. This is all based around, our design is all based around the thermodynamics.
So for the thermodynamics calculations, we're looking at three major heat sources. The first one would be directly from the fire into the module from the insulation. So heat is coming in from all 6 sides. We're trying to keep the inside cool as long as possible. That is estimated to be around 40.5 watts with our current design. The second heat transfer is coming from the hot air sampling that's taken in by our air intake design. So that's going to be a copper tube mounted on top of a heat sink, which is going to give us a constant temperature for that heat to dissipate, and our air is going to come out cooler so that the sensors withstand the temperature from the air. The final heat transfer, this one is estimated to be 32.7 watts with the current design. The final is the heat from electronics, the main one being the Intel board. From some testing, we measured the current and the voltage while running our software, and that equated to 18.6 watts. Now we came up to sum all these heat transfers, but we ignored the heat from the board because we completely insulated it with a layer of insulation from top and bottom, so that the power produced by it is not transferred to the rest of the module. Furthermore, we calculated with the amount of time we'd like this device to operate, the exact size of the heatsink, and we assembled everything together. So Daniel will talk about the assembling of the whole project.
All right. So there's several key components to make sure that it's fireproof. First, we have aluminum angle. Aluminum was chosen due to its low cost and its heat dissipation rate. So it's very good at dissipating the heat that we're going to have in the fire, because we don't want to be just absorbing all of it. The second is a foil-backed ceramic insulation. It's only that you see there. It's only about a ½ inch thick, so it doesn't provide much in terms of heat proofing, but it does protect from radiant heat that you have in a fire. So the walls are on fire and it's radiating a bunch of heat, and it does reflect a lot of that. In the next image, you're going to see the next set in the main fireproofing blocking, which is the next layer of insulation. It's also ceramic insulation, but it's 1.5 inches thick. So that basically blocks everything from the fire. You're not really heating anything past that. The last thing we did was to increase the robustness of our design. So if a beam falls on it, we don't want it to just cut through the insulation and break all our components. So we put a sheet of thin aluminum on all 6 sides, so that it's protected. Here's our fan and sensor assembly that's going to be mounted on the heat sink that Dan talked about. It has a very low power fan that we used about 10% of it, so it blows just a slight amount of air, and so that means that the air traveling through the copper tube dissipates into the steel plate before it hits the sensors. The 3 sensors you see there are the oxygen sensor that was donated to us by AlphaSense, the combustible gases sensor, and the oxygen sensor. The thermocouple was going to be...
You said oxygen twice.
Oh, did I say? Oh, I apologize. It was combustible gases, oxygen, and CO2, carbon monoxide, not CO2, carbon monoxide, CO. To determine the levels of oxygen and carbon monoxide, because that's what the firefighter is really worried about. In the next slide, you're going to see the heat sink assembly. It's a steel heat sink in order to absorb all the heat from the copper tube. The silicon that's used to attach it doesn't. It helps facilitate, in fact, the heat transfer, because it doesn't absorb or melt or be affected by the heat at all. In this next photo, you see this is our final connection between our hardware sensors and the software to verify that it was actually communicating correctly. In the next slide, you're going to see this is where we actually went to do our field assessment test. Before we came in, we we made sure that we put our Intel board in the bottom of the box. We insulated 2 more piles of insulation on top of it, so that's 3 inches of insulation on top to make sure that it wasn't getting any heat from anywhere. Then we put the heat sink on top of that, along with our sensor stuff, and piled more, and that was the final product. As you can see, there's some ceramic glass that we used to protect, that's heat-proof slightly to protect the webcams for the front and the back of the device.
So your next question is why the device is sitting here. There's 2 reasons for that. The one we're about to get into with our field assessment test, we can't test it with the fire here inside the building. The second reason is it was in an automobile that was stolen earlier this week, so unfortunately we don't even have it.
Yeah.
So,
Man, brutal.
So this is a picture of our programming flow diagram. We know that it's a bit complex. We'll be able to chat with that a little bit more technically a little bit later. And a list of our references. So what's going to take place now is Dayan's going to go ahead and load up the video. This video is going to be of our field assessment testing. So what we did is, as Daniel said, was we did the final assembly of the box, 2 layers of insulation, Intel board, 2 more layers of insulation, heat sink, all assembled into the box and screwed together and then placed into a surrounding fire. So this fire is on all 4 sides of it. This would simulate something inside of a burning structure. The video is about 5 minutes long. You'll see the fire kind of progressively starts small here, goes, and we have a graph at the end of it of exactly how the temperature changes. The captions that are going to come across the bottom will give you temperature readings at the 5, 10, 15, and 20 minute marks. The maximum temperature of the Intel board during this fire is going to be 160 degrees, still 160 degrees F, still operating properly, still remote access. Yes, ma'am. The heat sink actually changes only 2 degrees, which is perfect for our design.
Large thermal mass. What's this thing weigh?
So roughly 35 pounds. We actually didn't get a final weigh on it. That was once we got everything in it. The way the heat sink is designed, it's kind of a model of the actual heat sink. The calculations showed that it should be a solid piece of steel, but when we tested with kind of an array of a square tube together, it still dissipated all the heat that we needed to. So it is lighter in theory than our calculations would have shown it, because a huge block of steel would have been much heavier, compressing the insulation. But for our purposes, it actually worked out perfectly.
Also, keep in mind all of our calculations were done to the extreme maximums, and we ran this for a 30-minute period of time, and we needed to operate at about 15, so everything is practically double. So after all the testing, we can minimize the whole size of this module to be at least twice smaller.
So while the video is running, you'll be able to kind of keep up with the fire, how it's going, but Harsh is going to give you a chat about the programming that's taking place.
So in order for us to receive all the data and be able to read the live feedback, we wrote a proprietary application.
Speak up, Harsh.
Sorry. We wrote a C# proprietary application, and we are currently remotely accessing through the Intel Atom board, but we're having some lagging over here while we are remotely accessing. But we are also running it on the other laptop over here. As you can see, we are having live video feedbacks, and you get census data on each corner. Each data being assigned to a particular sensor. And over here, the firefighter can set a threshold before going into a fire. We're expected, for instance, expected oxygen rate is he's expecting expected carbon oxide. So while driving in, if the sensors reaches the threshold, the corresponding circles that illuminates, telling the fighters that it's not safe for them to go in. Feel free to interact with it. You can set the threshold right here, and it will show you the result.
So that's basically our project in a nutshell.
How does this thing get into the fire?
So based on our performance measures, we had a list of approximately 10. And the bottom 3 were associated with making the device mobile and getting it into the device. Time constraints, financial constraints. We weren't actually able to build a rover to get into the device. From the demonstration we saw yesterday, we were kind of talking about it over dinner, kind of laughing about it. That's perfect. The Modbot that they were demonstrating yesterday was a perfect application. Once it's heat-proof, to carry a device like this into a traverse at different sizes is kind of exciting.
The big statement is once it's heat-proof, which is not true.
Yeah, we're using similar structure for our device as the casing, so we can probably put insulation layers of just the same way we did this and calculate if everything will work out.
So what's the long tail here? Is that how you see it?
No, sir. It's the umbilical for the power. At this point, the battery is not inside the device, so we still haven't. The power consumption of the device is just 18 watts, and unfortunately, it's stolen before we got a chance to run the amp hour rating of how it operates in the fire. But right now, for this test, in order to ensure how it goes on it, we just ran the power cord to it and fireproofing as well.
How are you communicating to it then?
It's completely resolved through a network that we set up.
Through a router. And we reached about 70 feet through the router when we remote desktoped into the application. So that's far enough with this dinky old router for you to get most of the way through a typical house.
And this environment doesn't affect your wireless communication?
No, we had approximately 45 feet. The router itself was placed inside of a tin building, a tin roof building, a tin side building. While this is about 40 feet away from that building, we had no signal degradation whatsoever.
So the sensors, right now all we're seeing on our sensors is heat. What about the other things that you were talking about, like O2 and those sensors?
So with respect to the sensors, we verified, so separate from the Intel board, we verified that the CO sensors, the combustible gas sensors, and the temperature thermocouple were operating perfectly. The oxygen sensor was donated from AlphaSense, which is over in Europe, and unfortunately came to us uncalibrated. We struggled with it for a couple of weeks. The communication was a bit slow back and forth to them, and we did not get the oxygen sensor.
I just didn't see it in the demo. That's why I was wondering. Was it not in the demo?
The sensors were in the demo when we did it. It's all wrapped up in the box. There was no way, in order to test the situation, there was no way for us to kind of induce the combustible gas while the fire's there safely. So we were just kind of taking a temperature reading at the output of it and test the sensors separately from that environment. So we have proof that the sensors are operating properly, but inside the complete module, because there was no safe way to introduce combustible gas to a fire at the same time.
What was the cost of that sensor that you got donated?
From AlphaSense, I believe
It was $65.
Oh, okay.
And
So are these
No.
sensors fireproof as well?
they are not. That's the entire purpose of our heat sink, is to make sure, because we had to cool the air from approximately 1,000 degrees F. The air temperature is closer to 400.
Right. So you're going to bring the air into the box for
got
the
it.
sensor. That's what I was wondering. What are
You
your
got it.
sensors?
the sensor's
Yeah.
threshold is at 122 F. So as long as we keep it under 100, it was going to work. And the one you asked about was from Europe, yes, but it came also with a little motherboard because the design was very different, the MQ6 and MQ7, which are standard, and the whole thing was about $200.
Yeah.
Why do you need this for 3 sensors?
So the original design of the application was we were going to use the sensors, interface to the FPGA, have the FPGA communicate with the Atom board, and then to our proprietary program. So it's kind of a catch-all for us to be able to utilize everything simultaneously. So when we were using the FPGA, we were able to load a Verilog file that would take a digital input and give us a digital output to an LED, but we were not able to bridge that gap to get the communication into the Intel side of things.
So you weren't able to go from the FPGA into the microprocessor?
Correct.
Correct. The other reason,
We're hearing that a lot.
We actually build the application such that we have an output to an LED, which is on the board, and that's how we know that our program and software was running correctly. But we had to figure out either to monitor when the LED comes on or to change the output to a file or store it into memory somehow, and we were not able to find how that's made.
So how fast are you sampling these sensors?
Currently, there's a second delay between the data coming in.
So every 1 second you're sampling? I still don't see why you need this. Why can't I put a PIC microcontroller in there and be done with it?
well, first of all, it's because it gives you a Windows platform. Firefighters aren't technical people, so they need a platform that they're familiar with. So Windows makes it very easy for them to understand what's going on. The second reason is that we want to make the remote control part of it also part of this board. So in the future, when we attach that robot, we all want to run it through this board so everything's running off the same program. There's no intercommunication between multiple boards. So that would be the future. And so if we could get the FPGA to have bridged that gap, we were going to try to run some motors as well, just to prove the concept.
So stage 2 is getting that thing so it can be mobile and get into
Yes.
the fire.
And really the first half of our project, in the fall, that was our original design, was to design the ROV and the module together and to ignore the fireproofing. But once we came up with our performance measures and our system design, that would have been a complete failure, for us to go that route. Also with cost and things like that. So we kind of turned our attention away from the rover as much and focused in on the heat proofing, because that was such a critical point.
And that's novel, right? Where everyone's got a robot.
Precisely.
Correct. And so anybody can build the robot. It's been done a million times before, but we only found one instance where somebody had tried to do a fireproof analyzing type device, and that was actually Intel.
Yeah.
Although the rover would have to be problematic in that it can't go up and downstairs.
Yeah. Well, we were looking at a tank design for tank treads, because you could tank tread upstairs, but then you're talking about motors and the weight of the batteries, and so all that stuff was mechanical, and we're all computer.
I wasn't even going up a flight of stairs. I was going down two stairs with your family.
So I guess I would say you're a bunch of MEs playing in the computer space, but you're really computer guys. Because this is very, thermodynamic centric, right?
Yeah.
Very much so.
It was a
learned
big
a lot.
challenge overcoming the hotel. I had to go to NASA and work with them.
Well, that was the fun part of doing the project, was learning something we didn't know.
So is there a model where you can actually place the robot somehow instead of making it move? Are you thinking something like that? Like, so you have a portable robot that you can somehow place it without human intervention.
Sorry, I don't understand the question.
As in, the robot gets placed inside of fire instead of it actually finds its way.
So our thought process is that it would be
driven in by the firefighters.
Yeah, because the idea is to keep we want to save lives. That's the punchline. And so I need that firefighter as far away as possible. So the closest I want him to that building is the front door. I want him to set it by the front door, hightail back to the truck, and drive it in straight from the truck. Yeah. That way.
How long do you anticipate it taking to drive this through a burning house?
Depending on, that'll really depend more on the rover start, but we were expecting it to, just get it 20 minutes, to be able to inside. Time is of the essence.
Well, yes, I was going to say, if you drive that truck through my house after it's burning,
one of our performance measures.
I mean, if I throw a match in my house, it takes 15 minutes for the fire department to get there. 20 more minutes.
Yeah,
absolutely.
Yeah, and that comes from the research with the Houston Fire Department. We had a conversation with them, and they said they're not actually the first people to arrive at the scene. Is the fire chief himself who evaluates the situation. So they're like, we need a device that will actually see what's inside before we arrive, so that we're better prepared. And that's how we came up with the whole idea.
Interesting.
Yeah. Well, thanks for stopping by. We appreciate
you guys.
it.
Good work.
Yes, sir.
Thank
See
you.
you guys tomorrow.
Thank you very much.
One quick question: what year are you guys?
Seniors.
Yeah,
all of you?
We're all seniors. We're all graduating this semester, except for Hart. She graduates in the summer.
Great. All right. Thanks, guys.
Thank you.
Keep up the good work.
Yes, sir. Thank you.